Right. Okay. Welcome to our second session here, course yedu of our course, logic design and switching circuits. From the first lecture, we introduced the course. We talked of why. Number one, why are we doing this course? And we mentioned the need for representation of data. Communication involves sending signals, sending data. But how do you represent that information? We understand as we are talking, we can understand each other as humans, but the computers don't understand the language we speak. The mediums which transmit our information, they don't understand the voices, the messages, the text, the videos. They don't understand the pictures. There is a language they understand. And this course is concerned with the representation of that language. We introduced number systems. We introduced number systems, binary, decimal, octal. Did a little bit of manipulation of these number systems, how to convert between number systems. How to convert between number systems. We made conversions from binary to decimal and vice versa. Binary octal, binary hexadecimal, and octal hexadecimal. Lovejoy Murima, congratulations. You are the first person to be removed from this session. No report for this one. All right. And the message to everyone else, unless you are guaranteed your background, it doesn't have noise, and the one noise is automatically out. I think I mentioned the law of numbers. Too many numbers. I'm not okay with those numbers. So I'll have to be ruthless at times. All right. Today, we'll start with, where are we in Africa? We start with something I didn't mention, but I just went through it. Conversion of hexadecimal to decimal. Armazondo, congratulations. Right, hexadecimal to decimal. Let me share my screen. Multiple, nope. Okay. I'm hoping screen language are now visible. Right. So I did mention the process when I mentioned binary decimal conversion. I gave the process. You can use it everywhere. When you go from octal to decimal, hexadecimal, decimal, you use the same process for converting between number systems. I think this one is a bit tricky. That's why I needed to give attention to it. I think click is okay. Hexadecimal, mute yourselves. Hexadecimal, decimal. All right. Example, conversion hexadecimal to decimal. We had this one which we were using in our examples, I think I'll continue using the numbers which we were already using. Right, we made conversions from octal to hexadecimal using that hexadecimal number. Now we want to convert it to base 10. How do we do it? I think the process, I gave you the process. Basically, the process I gave you, you start your numbering 0, 1, 2, 3. Then you put your base 16, 16, 16, 16. This is 0. So the final number is the sum of all these numbers multiplied by those numbers. So we have 16 to the power of 3 multiplied by 3, which is 1496 multiplied by 3, plus 16 to the power of 2 is 256 multiplied by A. A, we said it is 10.
Just to show you the relationships.
What is happening here? All right, I need someone to give me feedback. Am I audible and can you see my screen?
Yes, and yes.
Okay, now we can continue. So 16 to the power of 2 multiplied by A. What is A in hexadecimal? A is 10 in hexadecimal. So plus we have 16 to the power of 1, that's 16, multiplied by 9 plus 16 to the power of 0, that is 1. 16 to the power of 0, that is 1, multiplied by F. F in hexadecimal, that is 15. If you add all these numbers, they give you 15007 base. Base 10. Basically, this is how you convert from hexadecimal to decimal, and vice versa. How do we convert the other way around? How do we convert the other way around? If you are given 15007 base 10, you want to convert it to a number base 16. The process is the same. I gave you the process from binary, successive divisions. Yes, successive divisions. So you divide 15,007 by 16. What do you get? I got 937, remainder 15. That is what I got. If you continue, you will get X remainder 9. Then you will get another X remainder 10. You get another X remainder 3. I guarantee you that if you continue these divisions, I didn't do them myself, but I guarantee you if you continue, you get these numbers. Then to put your number into base 16, we start with the MSB on this side, most significant bit, then we have the LSB on the other side. So this is 3, 10, A, 9, 15, F, base 16. That example was for those who didn't understand what I said when I talked of the process being the same for all the conversions. When you go from base X to base 10 or vice versa, base X to base 10 or vice versa, it's not the same when you go from base 2, when you go from base 2 to base 8. You don't do those successive divisions, successive multiplications. There's a process for that one. But if you go from base 2 to base 10 to base 10 or vice versa, if it involves decimal numbers, then the process is the same. Successive divisions, successive multiplications. And that's it for number conversions. We are done. Next thing, assignment and test. All right. Just to mention about just to mention something to do with your assignments and tests. Because of the numbers you have, I don't think it will be appropriate for me to put out assignments on WhatsApp and for you to send those assignments on email because it will be too much. ELMS is that function that you put assignments there and it automatically grades those assignments. So I don't have to do much of the work. So where am I heading? You need to register, ladies and gentlemen. You need to register. I don't think May, let me say mid-May. Mid-May, I will start giving out assignments. By then, you need to have registered so that you have access to ELMS, so that you will have access to your assignments. Recently, when we had our board meetings, there was an emphasis on following the regulations of the university. If you don't get plus 50% of all your assignments, you automatically fail. If you don't get plus 40% of all your practical work, you automatically fails. So I need for everyone to give much necessary attention on your assignments and your practicals. 50% coursework, that is the assignment and test, you fail automatically, even if you pass your exam. We have cases where people aced the exam, don't do their practicals, don't do their assignments, and they still pass. This is not going to be possible moving forward. So I think you need to pay much attention on your assignments and your tests. Right. Now we move on to binary addition. Manipulation of my number systems zethu. In arithmetic, we have addition, multiplication, and subtraction. So how do we add binary numbers? New page. We start with binary addition. How do we do addition? All right, it's simple. If you have 0, 1, 0, 1, 0, 0, 1, 1. If you have two numbers, A and B, and you want to add A plus B, what you get when you add 0 and 0, you get 0. When you add 0 and 1, you get 1. When you add 1 and 0, you get 1. When you add 1 and 1, you get 0, carry 1. So this is carry. So for this one, it's 0, carry 0, 1, carry 0, 1, carry 0. For this one, the sum, this is the sum, is equal to 0, and the carry is equal to 1. This is the basics. If you understand this, then you know binary addition. Example, we have two binary numbers, 1, 1, 1, 1, 0, 1, and 1, 1, 2, 3, 2, 3, 0, 1. We want to add these numbers. How do we add them? 1 plus 1 is 0, carry 1. That 1, you add it to this one. 1 plus 1, you get 0, carry 1. 1 plus 1. Now, for this third row or column, rows, column. This third column, we have 1 plus 1 plus another 1. You first add these two, 1 plus 1, it gives you 0, carry 1. This is the sum, this is the carry. 1 plus 1, 0, carry 1. If you add 1 to this, you get 1, carry 1. Let me repeat. So that let me give out a clear explanation of what we just did there. Right, I said we are adding 1 plus 1 plus another 1. If we add 1 plus 1, the first two, these ones, we get 0, carry 1, like this. No, okay. 0, carry 1. I think the carry is not supposed to be there. The sum. Okay, let's just put it there. That's the carry 1. If we add another 1, you get a 1, and this 1 at a carry, number 1. So it means if we add 3 more 1 consecutively, you get sum yako, you get 1, carry yako, you get 1. So for this one, 1 plus 1 plus 1, this is sum 1 with a carry 1. Now we have here 1 plus 1, sum 0 with a carry 1. My 1 and 3, if we sum them, we get 1 with a carry 1. If we add those, we get 0, carry 1. So basically, this is the sum of two binary numbers. I think the most difficult part is understanding 1 plus 1 plus 1. The rest is simple. This is sum 1, carry 1. Right, sum, carry. And that's it for binary addition. Mute yourself, comrades. Who is that? Kuda. Tiny what. Beware of whatever you are doing, my friend. Right. We have just a minute. Okay. And this is it for binary addition. I need to remind you this. These are the introductory topics. Simple stuff. You need to master them. You need to know how to add binary numbers. These are like the 1 plus 1. You need to know 1 plus 1 is equal to 2. Okay. But as we move forward, it will not remain as 1 plus 1 equals to 2. You will get your x and your y's and your z's. Then if you didn't understand 1 plus 1 is equal to 2, you will have difficulties understanding x, y, z. So make sure you understand this basic stuff, because as we move forward, it will definitely not be as much easy as A, B, C. All right, binary multiplication. We also have binary multiplication. Binary multiplication, same numbers. 0, 1, 0, 1, 0, 0, 1, 1. Right, Frederick Tangai Samanga, you just raised your hand. Question, comment. You can comment, Frederick, or question, Frederick Tangai Samanga. Nope, he doesn't want to comment. So we move on. I think if you don't understand whatever I'm putting out, you can raise your hand. I think I like that idea. You can raise your hand, then we'll give you the floor to participate. If not, I'll let you continue. Right, we are adding two numbers. No, we are multiplying two numbers, A and B. 0 times 0, it's 0. 0 times 1, 0. 1 times 0, 0. 1 times 1, 1. All right, we have a culprit with a noise. Voila, solved. All right, so this is it. If you have two numbers, A and B, and you want to multiply A and B, these are the values you get. So for example, if we have 1 0 1 2 3 1 0 1 0, we want to multiply these numbers. There is a trick we use when you do this multiplication sort of movements. I need you to take note of those movements. Watch. The first thing you do, you multiply the first number. When you have two numbers which you are multiplying, there is what? The multiplicand and I don't know the terms. But let's say we have this number A, we have this number B. Right. The first thing you do, you multiply the number A with 0. This is 0 on B. So if you multiply the number A with 0, we get 0 times 1, this first 2, 0, 0 times 1, 0, 0, 0, 0. That's the first thing you do. The next step, you multiply by this number, 1. You multiply A by 1. But where do you start? You don't start here. You put an X there, you start multiplication here. So the first one multiplied by the first one of A, you get 1. This is the first multiplication, rubber, eraser. Okay, this is the first multiplication we did. 1 times 1, you get 1. Then you have 1 times 1, you get 1. We continue, we have another 1, we have a 0, we have a 1. The next thing, you multiply by the next number, 0. Every component of the binary input, yeah, A, you have to multiply it by 0. Now you have two x's. As we multiply by this 0, we know automatically we get zeros everywhere. 0, 0, 1, 2, 3, 4, 5, 5 zeros, 0, 0, and another 0. Then we now have 3 empty spaces. We multiply by 1. When we multiply by 1, we get 1, 1, 1, 0, 1. I think so. After this, you then add all these numbers. When we add all these numbers, the first column, we get a 0. The second column, we get a 1. The third column is 0 plus 1, we get a 1. The fourth, 0, 1. 1 plus 1. 1 plus 1 is 0, carry 1. Then here we have 1 plus 1 is 0, carry 1. We have 1 plus 1 plus 1. This is 1, carry 1. Here we have 1 plus 0, we have 1. And lastly, we have 1. I can confirm this is the correct answer. This is how you multiply two numbers. What you need to take note of is these placeholders. You first multiply by 0, the last number, not 0 necessarily, but the last number here. If there was a 1 here, we would have multiplied this whole number by 1. But there is a 0. So we multiply by 0, then you put an placeholder, then you multiply by 1. When you come back, 2 placeholders, and you continue until you get your answer. Basics. Your job, my job was to show you the placeholder thing and everything else. Your job is to find examples and calculate the product of two numbers using the same method I am using here, or if you can find another method, okay, which is much simpler, it's fair and fine with me. What we need is an answer. I just like this one. It's much easier to explain. And that is it for multiplication. We move on to a binary subtraction. Binary subtraction. All right, example. All right, I think I'll need to mention complements. There is something we call complements in number systems. Complements, ones and twos. The complements, ones and twos, these are going to help us in doing manipulation, arithmetic manipulation of subsetting two numbers. Okay. Before we get into the examples, I think it's necessary to go through first what we call representation of signed numbers. I think I will have to hold on this one. I will have to hold on binary subtraction. I'll deal with this last. But we start with representation of signed numbers. When you talk of signed numbers, we are talking of the plus ones and the negative ones. Right. There are three ways of representing signed numbers. Three ways of representing signed numbers. One, we have introduction of what we call the sign bit. And the whole representation is called the sign bit magnitude representation. Sign bit magnitude representation. Basically, what this is if you have a binary number, for example, 0 0 0 0 1 1 0 0. If you have a binary number, we have two examples here. Let me give another one. 1 0 0 0 1 1 0 0. We have two numbers here. The most significant bit of these two numbers will represent the sign. Most significant bit represents the sign. In this format, MSB represents, running out of time. Okay, we have 10 minutes. MSB represents the sign. So when the MSB is 0, we have a negative number. It means the number is negative. If it's 1, we have a positive number. When we talk of MSB, most significant bit is this one. This is our MSB. This is our LSB. So in our examples, the signed bit is this one, the MSB. We have a 0 here, we have a 1 here. So it means number A, number B. Number A, it is a negative number. Why? Because it has a signed bit 0. A is a negative number because MSB is equals to 0. B is a positive number because MSB is equals to 1. Now, what is the whole number? How do you represent the whole binary number? A 0011. This is 8 4. This is 12, right? The first number is 12, but since it has a 0 as its MSB, it means it's a negative 12. If you are using number 1 representation, which is the sign bit magnitude representation, how do you present negative 12? You present it as in the form of A. Then the next one is positive 12. The first bit, the MSB, represents the sign. Then the rest represents the magnitude. So the MSB, if we remove this one, these are for the sign. Then the rest, we have magnitude. So the magnitude of these two numbers is 12, and the signs 0 and 1, negative and positive, respectively. This is representation number 1. Right. We have representation number 2. Representation number 2, new page. Ways of representing signed numbers. When we talk of signed numbers, that's positive and negative. Representation number 2, we have what we call ones complements. Ones complements representation. Representation. Right. The ones representation, one's complement representation of a binary number is done by inverting all its bits. You invert all the bits in a number. So for example, if you're given a binary number 0, 0, 1, 1, 0, 0, 1, 1. What is its one's complement? Its one's complement, if I invert everything here, I get a 1, 0 inverse to 1, 0 inverse to 1, 1 inverse to 0, 0, 1, 1, 0, 0. Invert. How do I write invert here? Invert. To get one's complements, you invert all the bits in a number. For example, typical example, you have 3 of 3 base 10 and negative 3 base 10. 3 base 10 to binary. This is a positive number, right? To binary, it is 84210011. This is 3 in binary. How do you represent negative 3 using one's complements? How do you represent negative 3 using one's complements? So this is positive 3. This is positive 3. How do you then represent negative 3? To represent negative 3, you invert all the bits in the binary number. So if I invert all the bits here, I get 1, 1, 0, 0. Base 2. This is negative 3 in representation ones. Yeah, let me do this. Ones complements. Oh, yeah. Ones complements. Don't confuse representation in one's complements in the normal representation of binary numbers. If I just give you this number from nowhere, I don't tell you what type of representation is. Someone else can say this is 84, this is 12, positive 12. I think we can agree. Binary representation of that number, it is positive 12. But when we talk of a representation in one's complements, it is negative 3. It's no longer positive 12. Right. Anything to add by one's complements? All right. In the one's complements format, the positive numbers remain unchanged. Positive numbers remain unchanged. So for example, positive 12, it remains unchanged. It's 1100. But when we go to negative 12, you invert all the numbers. The negative numbers are found by taking the ones complement. How do you take the ones complement? You invert all the numbers. So if I invert here, I get 0, 0, 1, 1. This is negative 12. Negative 12 is equals to positive 3 in 1's complement. 12 is equals to negative 3 in 1's complement. The confusion between a representation of numbers. You need to know the type of representation you are using. If you fail to identify the type of representation you are using, then it will be confusion all over the place. So if you're using 1's complements, what is negative 12? Negative 12 is the same as the normal 3 we use in BCD representation or the normal binary representation. And 12 is equal to negative 3 of the normal binary representation. But here, these values are for 1's complements. And I think that's it for 1's complements. Just to summarize for those who get confused quickly, 1's complements. 1's complement. Example. 3. Binary, normal binary. 3, it's like this. What is the 1's complement of this number? This is positive 3. The 1's complement, you invert all the bits. If I invert all the bits here, I get 1, 1, 0, 0. The 1's complement is a negative number. So this is negative 3. And that's it for 1's complements. Right. I think we've reached our 40-minute limit. So I think you all know the procedure. We stop the lecture, we end, then we restart after maybe 5 minutes. And that's it. Where is the end? Voila.